Hello guys, welcome back to another New Horizon Tutoring ACT video. Today we're just going to be going over some math again. Couple quick things I want to preface. I have a little bit of a bug, which is why I sound like this. So I apologize for that. I'll periodically be drinking water throughout. So again, I apologize. I'll try to project as much as I can. But yeah, we'll just work through that. It is kind of this season, I guess, of getting sick, and then also COVID, but I don't have COVID, so it's fine. But yeah, that's one thing. Other thing, congratulations on getting through another semester of high school. I'm pretty sure most high schools are either done with first semester or just wrapping up for winter break, which is awesome. I personally just had finals last week, and now I'm on winter break, which is great. So yeah, obviously I'm in a little bit different place. Actually, when we used to have classes in person, this is where we would have all the kids. It's a little bit different now, but it enables us to do this and film videos for you guys, so it all works out. There's silver linings. So yeah, that's basically all the intro I want to talk about. Other than that, like I said, we're just going to be going through some math. We're actually going to be working specifically on matrices only today, so just get out like whatever notebook you've been using, graphing calculator, something to write with, and then make sure you have your ACT Math packet with you. If you do have it with you, get it out. And yeah, I believe it's page 12. Again, like I said, we're going to be going over matrices, and we're not specifically going to have time, I don't think, to go through any problems at the end, but I will like intersperse some walkthrough problems throughout that. Basically, I'm just going to use those to explain concepts. Depending on what math you're in, I'm not sure if you guys have covered matrices yet. I honestly don't even remember if I covered them all that in depth in school. It might have been like algebra or geometry, so pretty early, depending on like how your high school specifically operates. But yeah, ACT is going to test you occasionally over matrices, which is why we have to cover it. And I would say the most difficult thing, which we're going to get to in a second, is multiplying two matrices by each other. And whenever I would get taught this, it never really clicked with me. I don't know why. So throughout the years as I've taught this, I've kind of devised a pretty good method, I think at least, that makes sense to most kids, for doing that. So we're going to go through that in depth, going through the basics with you guys, obviously, so you know how to apply it to problems. So yeah, we're just going to go ahead and get started. Like I said, just working out of page 12, starting with the basics with matrices and then getting a little bit more complex as we move on. Okay, so when we talk about matrices, obviously the first thing that comes to mind is, okay, what actually is a matrix? Why do we use it? Basically, the reason that we use matrices is just, it's a different way to organize numbers instead of listing them out randomly, right? So if we were just listing numbers, say 1, 2, 3, 4, that's probably what comes to mind when you think of listing. But with matrices, it's essentially just taking that information and arranging it in a different way. So obviously this isn't like the only form of a matrix. We're going to go over dimensions in a second, so I'll explain that. But yeah, like I said, basically it's just a different way to arrange numbers instead of just strictly using a list. Okay, so as we kind of give this loose definition, listing numbers in rows and columns, that brings up the whole conversation of dimensions. So dimensions are super important in matrices, and you're going to see why as we kind of work through the different problems that we can deal with matrices. But whenever we list the dimensions, it's just rows times columns. We're not like actually multiplying those numbers. It's like saying like a 2x4 piece of wood. Those are its dimensions, right? And it's always gonna go rows first and then the number of columns. So let's say we have a matrix like this, just numbers 1 through 6. As we can see here, rows are gonna be horizontal, right? Columns are gonna be vertical. Make sure you keep that in mind because sometimes if you work through problems too fast, you can kind of get that muddled. So just make sure that, obviously, you keep that in mind. But if we look at this, we can see that we have 3 rows, right? Row 1, row 2, row 3, and 2 columns, just C1, C2. So if we define the dimensions of a matrix by its rows times its columns, this specific matrix is going to be what we call a 3x2 matrix, right? Makes sense. Something else that kind of goes in with this, another way to think about matrices is that it creates a grid, right? Which it kind of does, because we have our rows across like this, and I'll use another color, our columns across like this, right? So each specific number has its own place, which is going to be super helpful to think of when we get to both adding and subtracting and multiplying matrices out. So if I'm saying like the value 1 is in placeholder row 1, column 1, or 4 is row 2, column 2, so on and so forth. Yeah, I think that's basically all I want to talk about with dimensions. Perfect. So yeah, again, that's just kind of the basics, laying out what matrices actually are, how they're arranged. Another thing that is important to know about matrices is basically all of the time, they're going to be represented by a capital letter. So like this is matrix A, or it could be B, C, etc. Not really something that you like have to memorize, I guess, but just be aware because that'll play into some of the practice problems that we go into, and that's just kind of like standard procedure with matrices. Okay, so like I said, that's just kind of the basics, laying it out. Now we're going to move on to part A, which is adding and subtracting matrices. Okay, so like I said, now we're moving on to adding and subtracting matrices. And this is the big sentence that is kind of going to dictate everything that we do with this. As soon as you kind of like understand this, it's pretty straightforward. But we're going to go through some kind of practice walkthrough problems just to show you guys. So this just says that 2 plus matrices can be either added or subtracted only if their dimensions match exactly. So what do I mean by that? Basically, let's say we have matrix A is, say it's a 2x3 matrix, and matrix B is also a 2x3 matrix. I'm not going to actually write them out because I'm going to do that in a second as we walk through our problem. But as you can see, obviously they have the same exact dimensions, right? Same number of rows, 2, same number of columns, 3. So that's how we know that we can add or subtract those 2 matrices. But even if their dimensions are just switched to a 2x3 and a 3x2, we can no longer add or subtract those 2 matrices because their dimensions don't match exactly, even though it's like super close. I'm going to show you guys why in a second. Okay, so let's say we have this practice problem, matrix A and matrix B, and we want to find A plus B. First thing we have to do is figure out if we can actually do this problem, right? Figure out if their dimensions exactly match. If we see we have 3 rows here and 1 column, so matrix A is going to be a 3 by 1 matrix. And if we look over here, it's pretty obvious to see right away, but we also have 3 rows and 1 column, so matrix B is also going to be a 3 by 1 matrix. Again, making sure that we're dealing with rows by columns, right? So since their dimensions exactly match, we know that we can add these 2 matrices up, and if you want to, you can like rewrite it out, but this one it's pretty straightforward to see. What we're going to do in order to add these two is basically just add both of the terms, since we're only dealing with 2 matrices, add both of the terms in the same exact placeholder. So that's kind of why I brought up the fact that it creates a grid, right? So in this specific space, it's row 1, column 1, and it's also kind of nice because there is only 1 column, so it's a little bit easier to visualize. But we have this value in row 1, column 1 for matrix A. And we have this value 4 in row 1, column 1 of matrix B. So what we're going to do is we're going to add whatever those 2 values are in the same space to create our new matrix. So whenever I deal with matrices problems, I always like to write my dimensions out for my new matrix. And when we're dealing with adding and subtracting matrices, the new matrix that we make is going to have the same exact dimensions as the 2 that we're dealing with, which makes sense, right? So again, 3 rows, 1 column. So if I want to find this new term in my new matrix in row 1, column 1, I'm just going to add those 2 values up there. So we have 5 here, and then it's the same exact procedure, again, pretty straightforward. If I want to find the new value in row 2, column 1, I'm just going to add the 2 terms in row 2, column 1 for both of my individual matrices. So it's 2 plus 5 is going to be 7. And then same exact thing for our last term. 3 plus 6 is going to be 9. Okay, so that's basically it for adding and subtracting matrices. The other thing that I do want to cover, however, or just kind of mention it briefly, let's say instead of adding these 2 matrices, we wanted to subtract them. First things first, procedure is the same. Make sure the dimensions match. We know they do, obviously. But now, since we're subtracting them, I mean, it's like you guys know how to subtract basic numbers, obviously. But just make sure that you keep that in mind, that you have to basically distribute that negative to all of these numbers here. So we have 1 minus 4. So then it would be -3, 2 minus 5, -3, and 3 minus 6. -3, which is kind of weird that it works out that way. But not really, because I chose really simple numbers. But yeah, just a reminder, make sure that you distribute or just do that operation to all of the numbers here. Okay, let me look at my notes. Okay, that's basically all I want to talk about for adding and subtracting matrices. Quick side note, I didn't really mention it before. Whenever you're working with matrices, you don't necessarily have to write out like row 1, row 2, row 3, column 1. You don't have to label them like that if it's not helpful to you. Like if you get it and it's just extra work, you don't have to. But I just find it helpful for like explaining and stuff like that. And if you do think it's going to be helpful for you for solving problems, by all means, go ahead. Okay, so obviously we just got done adding and subtracting matrices. I think that's pretty straightforward, not too difficult. Now we're going to move on to multiplying matrices. And there's essentially two different forms, I guess if you want to think about it that way, of multiplying matrices. The first of which is pretty straightforward. It's called scalar multiplication. And the second of which is called like the product of matrices. That's one of the most difficult things to deal with matrices, so that's kind of where we're going to spend the majority of our time. But yeah, first we're just going to go over scalar, and then we're going to go over product matrices. Okay, so like I said, dealing with scalar multiplication, it's really not too difficult. Really all it is the distributive property. So let's say in this example problem, we have matrix A, right here it's a 2 by 2 matrix, and we want to find the term 2A instead. So another way to think about it is that we have a 2 written out here in front of our matrix, and really all we're doing, as is kind of given away by the term distributive property, is we're distributing whatever value we're multiplying by the entire matrix. So each individual value. So then our new matrix is going to have the same exact dimensions, which makes sense, right? We're not really messing with that. So we make our little grid just to make sure we keep it straight. So then, like I said before, you just multiply whatever this is out here by each individual term. Make sure you put it in the right place. So this value, row 1, column 1, 2 times 1 is just going to be 2, obviously. And then same exact thing, be 4 here, 2 times 3, it's going to be 6, 2 times 4, it's going to be 8, and this is our new matrix. So, like I said, pretty straightforward, not all that difficult. It's nice because, again, we're not changing the actual dimensions. When we change the dimensions, it does get a little bit trickier. But yeah. It could either be like a number out here, it could be a variable, it could be a variable with a coefficient. So either way, just make sure that you're multiplying the entirety of what's out here by each individual value and keeping them in the correct space. Okay, so now we're going to be dealing with the product of matrices, which it walks through it pretty well on the handout that you've been given, but I'm just going to explain it a little bit more in depth, working straight out of that handout that you guys have. Okay, so when we work with the product of matrices, I like to think about it as a step-by-step process. So the first step is going to be check our dimensions. So when we're dealing with finding the product of matrices, checking our dimensions looks a little bit different than it does for adding and subtracting matrices, which, if you remember, adding and subtracting matrices, you can only do it if the dimensions are exactly the same. That's not the case with the product of matrices, and we're going to see why in a little bit. Okay, so there's this kind of little diagram on the handout that you guys have been given where basically it's just like representing two matrices here. This one has dimensions m by n, which if we were dealing with an actual matrix, it would have real numbers because you can't represent that. But it's just kind of using this for clarity's sake. So we have matrix m by n and matrix n by p. So the first step in making sure that we can actually perform finding the product of matrices is that the number of columns of the first matrix has to equal the number of rows of the second matrix, which makes sense, right? Because again, we have rows times columns, rows times columns. So that's one way to think about it, the fact that the number of columns of the first matrix has to be equal to the number of rows of the second matrix, or kind of like, not a shortcut way, but just like an easy visual reminder is that the middle two numbers are going to be the exact same. If the middle two numbers are not the exact same, you can't even do the problem, which sometimes is helpful in our case because it means we have to do less work. But in the problems that we go over, I actually want to show you how to do this, so it's not going to work out as nicely all the time. But yeah, that is the first step. And a little side note off of this, like based directly off of this step, it's going to be basically that the commutative property does not apply to the product of matrices. What do I mean by that? If you guys remember the commutative property, it basically is just saying that in like finding the product of two numbers or whatever, let's say we have 2 times 3. It's going to be equal to 3 times 2, right? Just because we switch the order of the numbers doesn't change the actual value. It's going to equal 6 both times. With matrices, that's not the case. And you may have already figured out why, but let's just apply it to this specific problem. So we're going to keep the dimensions of our first matrix the same, but we're going to switch the dimensions of our second matrix. Actually, no, I don't want to do that. We're going to do this. We're going to switch like the order of the two matrices. So instead of m by n times n by p, it's going to be n by p times m by n. Now, logically, our first step is to like check the dimensions, just like we did, right? Now if we check the dimensions, now that we switch the order of the two matrices, the middle two numbers are not the same. So therefore we can do this problem. And even let's say if we have like a 2 by 2 matrix by a 2 by 2, or a 3 by 3 by a 3 by 3, it would work both ways. Still, even if you switch the order of the matrices, you're going to get two completely different answers. So that's why the commutative property does not apply to matrices. So just make sure that, let's say, if it wants you to find the product of matrix A times B, you're finding the product of matrix A times B, not the product of matrix B times A, because like I said, commutative property does not apply and you're going to get two different answers. So that's just kind of like a side note off of this one specific step that we have to go through. Okay, so now that we have first checked the dimensions of our two matrices, making sure that we can actually find the product of them, what we're going to do is we're going to find our new dimensions for our final matrix. Because with both scalar multiplication and addition and subtraction of matrices, both times the dimensions stay the same, right? With the product of matrices, that's not necessarily the case, so we have to figure out what our new dimensions are actually going to be, and it's actually kind of a similar process to the first step, which is kind of nice. Okay, so basically what this shows is that when we're dealing with the new dimensions for our final matrix, our new dimensions for our new matrix is just going to be the number of rows of the first matrix. Again, if we just want to, label rows and columns here, makes it a little bit easier to see. It's basically just going to be however many rows are in our first matrix and however many columns are in our second matrix. And again, that makes sense, right? Because now we have rows and columns for the new dimensions of our matrix, which we always are going to write rows and columns. So very similar to the first kind of subset that we have to do in here, where you can either think about it as the number of columns of the first matrix has to equal the number of rows of the second matrix, or just the inside numbers. Same thing works here. You can think, okay, rows of the first matrix and columns of the second matrix, or you could just think about the outside numbers. Either way, we're going to come to the same conclusion. This one is just a little bit easier to visualize and remember in that way. Okay, so with this specific problem, since we have m number of rows of our first matrix and p number of columns of our second matrix, if we were, again, dealing with this hypothetical problem, our new dimensions would just be m times p for that. Okay, that's basically it for like the first two sub-steps, which aren't even like really getting into kind of the nitty-gritty of it. That's where the third step comes into it. That's where it gets a little bit more complicated. So now we're going to move on to that third step. Okay, so now our third step is actually going to be to find the values of our new matrix. And I can't really keep working with hypotheticals just because it gets way too hard to like conceptualize and understand actually. So I think the easiest way to show how to actually find the values and how to multiply the values out to get our final answer is just to work through a problem and explain it as I go along. So that's what we're going to do here. So we have matrix A. It's just going to be, as we can see, a 2 by 1, and matrix B is going to be a 1 by 2, and we want to find the product of matrix A and B. So first step, check the dimensions. As I said, we have a 2 by 1 here for our matrix A, and a 1 by 2 here. So, like I said, first step, check the dimensions. The number of columns of our first matrix has to be the same as the number of rows of our second matrix, or middle numbers have to be the same. They are the same, so we can go ahead and multiply. Second step, figure out the new dimensions for our matrix. It's going to be the number of rows of our first matrix and the number of columns of our second matrix, or just the two outside numbers. So the new dimensions for our new matrix is going to be a 2 by 2. So I'm going to go ahead and erase this and construct that. Okay, so another side note, just like I did for the other two, where I kind of, like, before I'm dealing with the actual values, I grid out the new dimensions of my new matrix and give however many spaces I need in there. It's all the more important for this specific kind of problem, finding the product of matrices, and we're going to see why in a little bit. Just make sure you give yourself plenty of space because there is a little bit more work involved. Okay, so now what we're going to do is, like I said, we're going to find the actual product of this. Sorry, just a sec. I have to make sure I didn't skip anything. Okay, perfect. I thought I skipped something, but I covered it earlier. Okay, so now what we're gonna look at is, like I said, multiplying the actual values. So this is specifically where I think it helps the most to write out like row 1, row 2, column 1, column 2, and you're gonna see why in a second. Because basically what we're gonna do is we're gonna multiply for this first term, which is in row 1, column 1, right? We're gonna multiply every term in row 1 of our first matrix by every term in column 1 of our second matrix. And I think that honestly, like, that logically clicks in my mind, just because again, we're dealing with rows by columns. So rows of our first matrix by columns of our second matrix. And now that's where, like I said before, this distinction of like, okay, this term is going to be in row 1, column 1. We're dealing with only row 1 of matrix A and only column 1 of matrix B. And it's really nice for this problem since we really only have 2 terms in there. But let's say like these matrices were bigger, you're just going to multiply every term by each other. So what we're going to do here is, like I said, take every term in row 1 of matrix A by every term in column 1 of matrix B. So that's what we're going to do. So there's only 1 term there. So we're going to multiply 1 by 3, and that is going to be, I'll just do it in black. That's going to be the first term in that specific spot. Now we're going to go ahead and move on to the specific grid of row 1, column 2. So we're still in row 1 of the first matrix, right? But now we're moving on to column 2 of our second matrix. So we have 1 times 4 now. And that's going to be that value in that specific spot. So now we're moving down to row 2 of our first matrix, right? So we're no longer dealing with 1. Instead, we're going to be dealing with this term in row 2 of our first matrix, which is 2. And since we're in column 1 for this first one, again, multiplying the value in row 2 of matrix A by the value in column 1 of matrix B. So it's just going to be 2 times 3. And then same exact concept. Now we're moving on to column 2. So the value of row 2 in matrix A by the value of column 2 in matrix B. So now we just have 2 times 4. And then basically we're just going to have to simplify that out, but it's just simple multiplication. So this is what our new and final matrix is going to look like. Okay, so I kind of realized that in order for you guys to get like a complete understanding of how to find the product of matrices, they do have to be a little bit bigger. I just wasn't sure if I was going to be able to go through a bigger problem just because it does take a little bit more time. So we have like 5-ish minutes left, which I don't think it's going to be enough time for me to do like an entire other problem. So what I think we're going to do is I'm going to go through the rest of my notes for matrices, which really isn't that much. It's just talking about what's called the determinant. And then next time we're going to go over a practice problem together of how to work through multiplying bigger matrices by each other, finding the product like we just did. But as the matrix gets bigger, or as the 2 starting matrices get bigger, it does get more complicated. So we're going to save that for another time. But yeah, that's just kind of an introduction to it. And next time I also will show you how to do it on the calculator, which is, it's important to know, right? Just because depending on the specific problem, it can be more efficient to do it on your calculator instead of trying to do it by hand. But let's say instead of numerical values in here, they throw in variables. You can't do it on your calculator, which is unfortunate, but that's why we kind of have to know the longhand way to do it. Okay, so like I said, kind of moving on from this, but we will revisit it next time with a practice problem and then move on to everything else we're going to do in that session. But for now, we're just going to finish up our notes for this and then call it a day. Okay, so the next and final thing that we're going to deal with matrices is what's called the determinant. And you really don't have to know like what the determinant is necessarily used for, just because the ACT goes pretty surface level on how in-depth it goes for this. But basically it's just used to find an inverse of a matrix, which you might go more in depth in like your high school math classes, but we don't have to now. But just know that that's technically what determinants are used for. So yeah, and let's say we have this kind of like practice matrix, where it's A is equal to a 2 by 2 matrix. They can either write out like find the determinant of this matrix, or they can write it like this, where it basically just looks like it's absolute value signs of whatever that matrix is called. But it's not absolute value signs, it's the determinant. So make sure you keep that in mind, make sure you're looking for that on the actual test. But the way that we find the determinant, if you see this or if it tells you to find the determinant, is pretty straightforward, and you only have to worry about it for a 2 by 2 matrix. It is possible to find the determinant of like a 3 by 3 matrix, but it's a lot more complicated. The ACT doesn't ask you to do that, which is kind of nice for our sake. But it's kind of like a formula, I guess, that you just have to remember. And it's essentially just going to be AD minus BC. So it's kind of like you're cross multiplying and finding the difference between the two. And then most of the time, these will be actual numerical values. So let's just do a practice one. Let's say we have matrix A, again, a 2 by 2, just 2, 4, 6, 8. And it asks you to find the determinant of this matrix, just like we did up here. It's going to be these two values in the place of AD times each other, and then subtracting these two values in the place of BC. So it's going to be 2 times 8 minus 6 times 4. So then if you multiply that out, it's going to be 16 minus 24, which is negative 8. Awesome. Okay. So yeah, that would be technically the final answer for that. And that's basically all I want to go through with matrices today. So good work. Matrices are kind of a outlandish concept, I guess, just because we don't deal with them all that often. But since they are covered in the ACT, they are still really important to go over to understand. And again, like I said a couple minutes ago, we're going to go through one practice problem of a little bit more complicated product of matrices next time. But yeah, other than that, we're going to call it a day. Really good work, and we will just see you with another video next week.